or any queries, you can always get in touch with me. So, so first of all, I'd like to congratulate everybody for Asteroid Day, which is what we are celebrating, which is celebrated on the 30th of June every year. And this is a UN-sanctioned day of public awareness of the risk of asteroid impacts, some of which I will cover in today's talk. And it's observed annually to mark the date of the Earth's largest asteroid impact in recorded history, which is the Siberia Tunguska event, which took place more than 100 years ago in 1908. You can see this whole region, which was almost cleared up more than 100 years ago, and this is still how it looks like even now today. And that's what we are kind of commemorating. So let's get on to the main topic. What are asteroids and where do they come from? Right? So a long time back, about 5 billion years ago, the solar system was actually formed. And like you see in this animation, you had basically what is called the solar nebula, or this is the sun which is forming at a very young age. And you have, this is the disk, protoplanetary disk, which was around the sun. This was gradually rotating. And as you can see that as it rotated and the sun was born, by the sun being born, I mean the sun started off its thermonuclear reactions. You had regions in this protoplanetary disk where accretion takes place, coalescence of material, and where you actually have the formation of planets taking place. So you can see that as a planet forms, various planets form in their orbit, it almost clears up the debris which is around it, and you have the solar system being formed. So you have the young sun and you have the solar system being formed. And what is the solar system basically? It's made up of our star, which is the sun. And then you have the 8 planets going around it, all of them bound by gravity. So you have the planets Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. You have the dwarf planet, which is Pluto. You have dozens of moons. And we have millions of asteroids, comets, and meteorites. So therefore, asteroids, comets, meteorites, these are all part of the solar system, which were actually formed since the time of formation of the solar system, which are very much part of the solar system, right? So minor planets, what do we basically mean by minor planets? Minor planets, they include asteroids. They include near-Earth objects, Mars crossers, main belt asteroids, Jupiter Trojans, as well as distant minor planets, for example, Centaur stars, Neptune objects, most of which reside in the Kuiper belt and the scattered disk. We'll come about it in a bit. And there are millions of asteroids ranging in size from hundreds of miles to several feet across. And in total, but if you were to actually look at this in total, you would see is that the total mass of all the asteroids is less than that of the Earth's moon itself, right? So you have, that is the kind of mass which is sitting in this mass of asteroids, right? So that's what asteroids are. But why are asteroids so important for us to study? So the first important thing about asteroids is that this is actually remnants or residuals of the solar system when it formed, right? So therefore, it obviously contains a lot of, where you can actually keep amino acids for a very long time, and they can travel all through space, but then they can disperse life-giving material on to different planets. And asteroids, which we can come to a bit, they are also the possible bearers of water to the Earth. Another very important thing about asteroids is what we are celebrating Asteroid Day for itself is the impact of asteroids. And therefore, they need to be monitored, as impacts by asteroids, they can actually cause mass extinction of life on the Earth. And therefore, for our very survival, it's very necessary that we actually know about asteroids as well as the possible impacts which can take place from asteroids. Another possible offshoot of this is also mining, because a lot of asteroids can have a lot of rare materials on them, which can actually be, there could be mining. That's what people are actually talking about, where we can mine very rare metals and materials from them. Now, where are asteroids formed? So if you look at the model of our solar system, here you have the sun, you have Mercury, Venus, Earth, Mars, and typically the region between Mars and Jupiter, right? That is where you're going to have the asteroids. And along with that, there is something called Lagrange points. So Lagrange points are the points where the gravitational force gets balanced. And there are different kinds of Lagrange points. For example, there are Lagrange points which are made up, which are the Lagrange points for the Sun and Jupiter, because we know that in our solar system, the most massive planet is Jupiter. And if you look at these things, you have these 2 points over here, which is exactly at the location of Lagrange points, 60 degrees. And you have, these are what are called 60 degrees ahead. You have Jupiter over here, 60 degrees, and 60 degrees behind Jupiter. You have the Lagrange points, and you have these Trojan asteroids, which actually belong to this region, right? Other planets also have a few Trojans which correspond to their Lagrange points. For example, Neptune has 30, Mars has 9, Earth and Uranus each have 1 that science have identified to date. So these are the ones which are sitting at the Lagrange points corresponding to that planet. And possible that many of the solar system moons were actually once asteroids. These are typically the moons, for example, likely candidates are, for example, Mars moons, the moons of Mars, Phobos and Deimos. They are very unlikely satellites, and they are most probably asteroids which were captured by Mars. So as Mars was going around in its orbit, and you have the Saturn, Uranus, Neptune. Most of these should have also most probably been asteroids. Now we can actually classify asteroids based on their semi-major axis, where, for example, you have the Amor asteroids, which have orbits that approach the Earth's path but remain exclusively between the Earth and Mars. You have Apollo asteroids that have Earth-crossing orbits but spend most of their time outside the planet's path. 18 asteroids, they also cross the Earth's orbit but spend most of their time inside the Earth's orbit. And then you have the Atira asteroids, which are near-Earth asteroids whose orbits are contained within the Earth's orbit. So depending on their semi-major axis or the position of the orbit, we categorize them into these various kinds. And as of October 2021, scientists have discovered more than 20,000 near-Earth asteroids. And of these, just under 10,000 have diameters which are larger than 500 feet. Okay. Now, how do we generally find asteroids? How do you locate asteroids? So in the year 1801, while making a star map, Italian priest and astronomer Giuseppe Piazzi, he actually accidentally discovered the first and the largest asteroid which we know, which is called Ceres, which orbits between Mars and Jupiter. And today, since Ceres is a very large asteroid, it's actually put into the category of what are called dwarf planets. And it actually accounts for a quarter of all the mass of the known asteroids in or near the asteroid belt. And since about the year 2000, NASA has actually, so this was the accidental discovery of Ceres, but after that, since the year 2000, more than 20 years back, NASA has actually spearheaded a campaign to identify and track near-Earth asteroids. So there are various programs which are conducted. For example, the Catalina Sky Survey in Arizona and the Pan-STAR telescopes in Hawaii. They actually specialize in identifying these objects and have each discovered thousands of asteroids, right? So now the number of asteroids known is very, very large. Now, how do these form? Like I explained to you all in the very beginning, that asteroids are essentially leftovers from the formation of our solar system, which is 4.6 billion years ago, right? And then what happened is that Jupiter formed, which is a very massive planet. And the birth of Jupiter actually prevented any planetary bodies from forming in the gap between Mars and Jupiter, right? And therefore, what you see is, if you can see in this area, I showed you this area between Mars and Jupiter is where we have the asteroids. And that's essentially because of the presence of Jupiter, because it's so very massive. And you could not have the formation of any other object in that region because of the presence of Jupiter. And these small objects that were there, they collided with each other, fragmented, and formed what is called the asteroid belt, right? Now, there are various theories or understanding of how actually the solar system formed. There are two leading models called the Nice model and the Grand-Tack model. And in both these models, they actually support what is called planetary migration. That means that the planets like Jupiter, etc., actually formed in another region, and then they actually moved, they were more inwards, and they actually moved outwards. Okay, and this planetary migration which actually took place, this actually could have set asteroids from the main belt raining down onto the terrestrial planets, emptying and refilling the original belt. So because of that, because of this planetary migration which took place during the formation of the solar system, that's why you actually have these planets, these asteroids spread out all over the solar system, basically because of planetary migration. Now, what are these asteroids like? Now, typically asteroids are irregularly shaped, and though they are close to spheres, but Ceres is nearly spherical, not very spherical. But otherwise, the bulk of them are often full of craters. There are pitted, there are pits in them. For example, Vesta is a very well-known asteroid. It has a diameter of about 460 kilometers, and most of these surfaces of asteroids are actually covered in dust. They are irregular, dusty kind of objects, right? And the average temperature on the surface of a typical asteroid, it's obviously very low, it's very cold. It's minus 100 degrees Fahrenheit, or which is approximately minus 73 degrees Celsius. And asteroids in that way have stayed mostly unchanged for billions of years. That is the period of the formation of the solar system. And therefore, research into asteroids can actually reveal to us a great deal about the early solar system. What was the early solar system like? What was the material like? And what were the conditions like? Now, as asteroids revolve around the sun in elliptical orbits, they also rotate. So there is revolution coupled with rotation. You have a double kind of motion which is there in asteroids. And more than 150 asteroids are actually known to have small companion moons. Some of them have even more than one moon. They could even have two moons. As well as you could have some asteroids which are actually binaries, or even part of multiple systems, right, of double asteroids, etc. And often you could have two asteroids of roughly equal size orbiting each other. Similarly, there are even a lot of triple asteroid systems, like I said, multiple body systems. So what we see is asteroids actually come in a variety of shapes and sizes. Some are solid bodies, some are actually like piles of rubble bound together by gravity. And some of them are actually known to have even rings and tails. Some have moons, right? So asteroids by themselves are also very interesting objects to see for this large variety which you have in shapes, in sizes, etc. And then what are the types? Even in composition, we see that there's a wide range of types of asteroids. So you have what are called the C-type asteroids, or the carbonaceous ones. These are basically made up of carbon. They are grayish in color, and they're the most common kind of asteroids which you have, which actually includes more than 75% of the known asteroids are all C-type or carbonaceous. They probably consist of clay, stony silicate rocks, and inhabit the main belt's outer regions. The other kind of asteroids are what are called the S-type, or the ones which are made up of silica. So the silicaneous asteroids are greenish red in color. They account for about 17% of all the known asteroids, and they dominate the inner asteroid belt. So in the inner asteroid belt, you have the S-type things. The outer one has the C-type, and they appear to be made up of some kind of silicate materials and nickel-iron kind of composition. The M-type asteroids are the ones which are metallic. Okay, they are essentially reddish in color, and they make up the most of the rest of the asteroids, and they are essentially found in the middle region of the main belt. And essentially the metal they are made up of is nickel or iron, and that is the composition for the M-type asteroids. And then there are there are many other asteroids which are, like I said in the beginning, made up of even rarer elements or rarer metals. And for example, some of them, there is an asteroid called Vesta, which actually has a basaltic volcanic crust. Okay, and that's the kind of composition which we have of asteroids. If you were to actually look at the the distribution of sizes of asteroids, that's very important for us, because when we are talking about impacts from asteroids, the most important parameter for the asteroid is the size of the asteroid, right? So if you can actually see, Obviously, as you increase the size of asteroids, this is in kilometers, say 1,000-kilometer asteroids, you can see that the numbers are very small, right? But why, if you're looking for a larger size, say a 1 kilometer kind of this thing, then obviously the number of you could have a million asteroids which could have a 1 kilometer diameter. But for example, if you're looking for a 10 kilometer kind of if you're looking for, say, a larger, say a few hundreds kilometer, then you could be just about in the tens, right? So what happens is, if you look at the largest one, which is Sirius, which we spoke about earlier, this has a diameter greater than 900 kilometers. But for example, as we go to the smaller sizes, you can see that the numbers gradually, as the size increases, the numbers fall, right? The numbers are much larger for smaller size asteroids, which is good for us. So for a few asteroids, let's just compare their parameters. For example, Ceres, which is the largest known one, the diameter is about 27% that of the moon, which is pretty large. It's about 964 kilometers, right? It's not exactly a circle, but it's somewhere close to that. It has an orbital radius of about 2.7 AU and a period about 4.6 years. You have a slight ellipticity in the orbit, while you have some other asteroids I've mentioned over here, Vesta, Pallas, Hygiea. These have also diameters which are reasonably large. These are 400, 500 kilometers, and they have distances of about 2 to 3 AU with orbital periods about 4 to 5 years, right? And their densities, you can see, range from about 2 to 3 to 4 grams per cc. That's the kind of density we have for the largest of asteroids which are known. Now let's come up with the most important question, that can asteroids actually hit the Earth, right? And obviously the answer to that is yes. So ever since the Earth formed about 4.5 billion years ago, asteroids and comets have routinely slammed onto the planet. And the most dangerous of the asteroids that hit the Earth are obviously extremely rare. We just saw that the previous slide, that as the size increases, the numbers fall drastically. So an asteroid capable of a global disaster, for that you would have to have an asteroid which is more than 400 meters wide, right? And that kind of an impact. So what actually happens when an asteroid hits? The impact would actually raise enough of dust into the atmosphere, and it would cause what is called a nuclear winter. So what happens is that if the dust goes up into the atmosphere, the plants are unable to synthesize, do photosynthesis and create these things, and therefore the creatures who actually live on the plant life, they do not survive, which actually results in the extinction of the creatures who survive on those creatures, right? So essentially, some of the extinction is because of a direct impact. But if the direct impact, 400 meters will not cover the whole Earth. So that will just be a portion of the Earth. But the resultant in the form of the nuclear winter, which will actually blanket the whole Earth in such a way that the plant life will not be able to survive, that will lead to the fall of the animal life, which depends upon the plant life, right? And that's the kind of result which you have by an asteroid impact. So what is a near-Earth asteroid, right? And this is the kind of impact which actually took place 65 million years ago, which actually led to the extinction of the dinosaurs, which is what we call a nuclear winter, right? Which actually led to this dusty atmosphere all over the Earth, where the plant life could not survive, and therefore dinosaurs living on plant life could not survive, which also resulted in the extinction of the dinosaurs which lived on the other dinosaurs, right? So that actually these things are. So an asteroid is called a near-Earth asteroid if its trajectory comes within 1.3 AU of the Sun, and that means within 0.3 AU of the Earth's orbit. Now, in astronomy, we have a unit called an AU. An AU is an astronomical unit, which is the distance from the Earth to the Sun, which is 150 million kilometers, right? So that is a near-Earth asteroid. While a near-Earth asteroid is supposed to be potentially hazardous, which is a PHA, a potentially hazardous asteroid, if its orbit comes within 0.05 AU, right? So near-Earth asteroid is within 0.3 AU, but it is hazardous if it comes within 0.05 AU, okay? Which is approximately 19.5 lunar diameters, right? So about 20 times the distance of the moon, that's when it is the so-called Earth minimum orbit intersection distance, and that is when you can have this potentially hazardous asteroid. Now, there was a very well-known Netflix film which was released just this year called Don't Look Up, which is a very nice movie, and it basically picks up such a hypothetical event where you actually had a PhD student doing astronomy who was observing using the Subaru telescope. She was observing some other kind of objects, and that's when she detected this asteroid. And it was known that this asteroid is going to come and impact the Earth within 6 months. And it's a very good movie. I would recommend this movie to many people to actually see it, because it very well describes how in our present society, where science awareness is very limited, when you have these two scientists, the PhD student and a supervisor, who are trying to convince people about the threat that's going to happen because of the imminent impact which is going to happen, and how at that point of time, socially, uh, countries and the politicians, etc., they do not realize the importance of the event, and how very unprepared we are for such an event if it could possibly happen. So, like I mentioned, despite their size, asteroids can be dangerous, and many have hit the Earth in the past. More will crash in the future. And that's one reason why scientists need to study asteroids and eager to learn more about their numbers, orbits, etc. Because if an asteroid is headed our way, we better know about it, because there has to be some kind of preparation which we need to be doing for that event. So this movie very beautifully covers it and describes how unprepared we are in present times for such an event. Now, smaller asteroids are believed to actually have to strike the Earth every thousand. Yeah, so an asteroid of that type, of the one described in Don't Look Up, is obviously a very rare kind of phenomena which would take place. But smaller asteroids that are believed to strike the Earth every 1,000 or 10,000 years, but even such an asteroid could actually destroy a complete city. It could cause devastating tsunamis, and but if you have space rocks which are smaller than 25 meters, what happens is when they enter the Earth's atmosphere itself, they burn up, right? That's what we call shooting stars, which you actually see light up in the sky in the nights. But if they are larger size and they finally manage to fall onto the Earth, then you really have a large thing. So the most recent impact we had is what happened in February 15, 2013, where an asteroid actually, it was not a very large asteroid. It's about 20 meters across. And what it happened is it fell on the Russian city of Chelyabinsk, and it actually created a shock wave. So you had this asteroid falling in, and then you had a shock wave that injured about 1,200 people, and it shattered glasses and created a lot of devastation in that area. Okay, this was not many years back, about 9 years back. Now, what is a meteorite? So when an asteroid or a part of it actually crashes onto the Earth, if it falls on the surface, that's when it's called a meteorite. It is a meteor as long as it's up in the sky, it's a shooting star, right? If it burns up in the sky, it is called a meteor. But if it actually hits the surface of the Earth, it's what is called a meteorite, right? Now, typically, so they are found on the Earth, which are, rocks of a strange origin, and that's why they are easy to identify. And they can be of different kinds. There are what are called iron meteorites, which are made up of iron, nickel, cobalt, etc. There are what are called stony meteorites, which are made up of oxygen, iron, silicon, magnesium, aluminium, as well as nickel and calcium. So they have typically compositions of this kind. These are the ones that we have actually found on the Earth, the meteorites. Now, while we were talking about this whole problem about impacts from asteroids, causing devastation on the Earth and causing mass extinctions, etc., we also have to realize that even water on the Earth, right? When the Earth formed, the Earth was actually dry and barren. Okay, and as per our present understanding, it's only through asteroid and comet collisions that could have actually delivered water, ice, and other carbon-based molecules onto the planet. So this is what was essential for the planet. Number one, for life to survive in the form of water. And number two, this is also one of the possible explanations of the origin of life itself, where it's possible that the origin of life on the Earth's surface itself could have happened because of these impacting comets, etc. And that's where you actually get, you know, where you get this. So, and this is known because, for example, in 2009 itself, there was this thing called Themis, on which actually water ice was confirmed using the infrared telescope facility. And therefore, we know that there is a large amount of water ice rather, which is present on these asteroids and comets. And that is essentially the origin of this for the Earth. So it's not that asteroid collisions or comet collisions are such a, you know, devastating factor. For all you know, they could be the very reason why we are alive and we do have life and water on our planet. So so in principle, these impacts are also they are something which is very essential for our survival. Now, the question is, how can we actually protect the Earth from asteroids? And the simple answer to the question is we can't, right? Because while you have these asteroids coming in, it's very difficult to, for example, for every known asteroid, asteroids are not radiating surfaces, right? They reflect light. And therefore, depending upon the position of the asteroid, we typically only see asteroids in certain regions of the sky where light falls. While the unlit part of the sky, we do not see the asteroids over there. And therefore, definitely for the ones that are known, there are many that have not been spotted, which we've not even identified. And so one of the simplest way of observing them is using a radar. So if you use a radar, so in September 2017, there was this asteroid called 3122 Florence. It cruised the Earth at about a distance of only 7 million kilometers, which is 18 times the distance of the Moon. If you remember, this is what we call potentially hazardous asteroids, PHAs. So this is a PHA. And but the flyby confirmed its size and rotation period. And basically through radar observations, we actually got information about its shape, the presence of one crater, as well as the fact that it actually had 2 moons, this asteroid. And then in a NASA broadcast earlier in 2017, Marina Brozovic, who's a physicist at JPL, Jet Propulsion, said radars can actually reveal a lot of details about asteroids, whether it is its size, its shape, whether it's a single or a binary object, and it can actually give you a lot of information about asteroids. Other than that, we've been much more adventurous, and we've actually since the idea is to actually study these asteroids, there have been various missions to asteroids, right? So one of the missions, which is the most recent mission, was called the DART mission. And the DART mission was actually launched in 24th November 2021, very recently. And DART actually stands for Double Asteroid Redirection Test. And it was actually a test made by NASA to actually test whether can we actually do some kind of a planetary defense mechanism against these near-Earth objects. So we just see what is the DART mission about. So what it actually did is it was launched by the Falcon 9 rocket, okay, built by the Johns Hopkins Applied Physics Laboratory. And what it basically does is it will navigate a spacecraft to go to a target asteroid, intentionally collide with it, basically to deflect it, okay? And the idea was to actually test whether if we have an asteroid which seems to be aimed towards the Earth, can we actually do such a thing where we can launch a mission which can actually, push the asteroid off from its path to stop the impact. And there was a CubeSat which was riding with DART, provided by the Italian Space Agency. And that was basically meant to capture images of the impact and the resulting cloud and look at it. So if you actually see this more carefully, you have this double asteroid system, which is made up of Dimorphos and Didymos. So there are these two things. And DART was on a one-way trip, so it went straight to this. And it actually aims straight at Dimorphos, okay, which is an asteroid is about 160 meters across, okay. And this Dimorphos actually orbits Didymos, okay. And it orbits it at a much slower speed relative than the pair orbits. And the interception time is supposed to happen soon, which would be between September 26th and October 1st this year, 2022. And the mission has to actually impact or hit onto dimorphous, and it is expected that the kinetic impact of this impact will actually deflect this thing from its path. And the idea is actually checked whether this method, you have this Lycia cube, which is the CubeSat also, which will take the images, and it will actually see whether are we in a position to actually protect our planet from future threats in doing a mission like this. So it will give a not so gentle nudge to Dimorphos and this thing. Now, this is a very interesting project, but the first spacecraft to actually take close-up images of asteroids was NASA's Galileo, which is way back in 1991, which also discovered the first moon to orbit an asteroid in 94. After that, in 2001, Hayabusa mission, which was the first spacecraft to land and take off from an asteroid when it visited the near-Earth asteroid Itokawa. And the spacecraft had a series of technical glitches, but it did return a small amount of asteroid material to Earth in June 2010. NASA also had another mission called the Dawn mission, which was launched in 2007, which went straight to the asteroid belt. Okay, it explored Vesta. Vesta is one of the asteroids I mentioned earlier. And after a year of work there, it left the asteroid for its trip to Ceres, which is the other large one. And it is the first spacecraft to visit Vesta and Ceres. And the mission ended in 2018 when the spacecraft ran out of fuel, but it will continue orbiting Ceres for another 50 years. Now, like I told you, Hayabusa 1 was sent, but then Japan sent another mission called Hayabusa 2, which was the second asteroid sample return mission, like Hayabusa 1. And the spacecraft actually visited a near-Earth asteroid called Ryaku and studied the body for about 18 months. And this work included deploying a small hopping rovers, blasting the asteroid with an artificial crater. And in December 2020, 2 years ago, Hayabusa 2 actually delivered pieces of Ryaku to Earth for scientists to study. NASA also flew its own sample return mission, which was called the Orisis Rex, which actually the spacecraft is now trekking back to Earth, and the delivery is expected sometime in 2013. In September 2013, we expect delivery of the material which makes up the asteroid launched. 8 different asteroids. So Lucy will actually visit a main belt asteroid as well as 7 Jupiter Trojans asteroids, which orbit, which I think I showed you the Trojan asteroids, and they'll all be flyby encounters to basically study them. So the Lucy mission, if you can see it over here, I told you had Jupiter, and 60 degrees before and after the satellite, the planet, you have these groups of asteroids, which basically lie at the Lagrange points. And what Lucy will be doing is Lucy will actually, it has been launched, it's going to observe these Trojans and then check out the other Trojans, right? So it has 2 close Earth flybys before encountering its Trojan targets. And in the L4 cloud, which is the Lagrange cloud, Lucy will fly by a series of satellites. I won't mention the names. And as a bonus, in 2025, on its way to L4, it flies by another asteroids. And so you will have this kind of cycling taking place every 6 years, which Lucy will do between these Trojans, right? So this is also a new mission, which is actually doing this. Psyche is also a planned orbiter mission, which will explore the origin of planetary cores by studying the metallic asteroid of the same name. So this is an expected mission, which is expected to be launched this year itself. So this is a kind of a successor to Lucy mission, etc., which will actually study these by studying metallic asteroids. And this will hopefully be launched very soon in September 2022. Right. Now, another thing which I was talking to you about was, can we actually mine asteroids? In the movie Don't Look Up, it is shown that the president of the country actually is advised by her corporate advisors to actually when they know that the asteroid impact is going to take place, they instead tell her that the most important thing about the asteroid is not the disaster, but it's the fact that they can mine the asteroid, because the asteroid has a bunch of precious metals on it, which would be very useful to mine and actually get. And therefore, there are a whole bunch of companies which have actually started exploring these ideas. You may have seen a lot of these things even on the internet about people actually looking for, asteroids made up of diamonds, that they could, mine diamonds on asteroids. And for example, all kinds of rare metals, whether they could be mined from asteroids. And so the ideas, possible ones, is that water can be processed into a rocket propellant to save the spacecraft from needing to launch the weight of their own return fuel. And there are various such possible suggestions or possible plans that people do have about mining asteroids. If you actually search on the net, you will find a whole bunch of so-called companies which seem to be have been launched, which actually have agendas of this kind, where they actually think that we can actually find a sustainable supply of natural resources by doing fuel exploration in space, and by doing asteroid mining. And um, and therefore there are whole, like I said, so some of them are the water rich ones, because people even think that obviously water is precious enough for us to want to try to get that from space, right? Other than that, there are a whole set of platinum group materials, okay, platinum group metals rather, which are easily found on asteroids. And obviously on the earth, the abundance of these metals is very, very low. And therefore, if you were to actually look for them from asteroids, you could obviously get it, which will actually, like you see the benefits over here. They say it would reduce the cost of electronics, it will be used to electrify transportation, to drive innovation, create a cleaner earth, etc. And so if you had just one single 500-meter platinum rich asteroid, it would be worth about $2.9 trillion. And since 1 ounce of platinum is valued at about $1,500, and that would be more than the yearly output of platinum, right? And therefore there are a whole bunch of companies or prospective entrepreneurs who actually think that this is something that they need to explore and actually look out for in terms of asteroid mining. Now we'll come on to another important section. Is we spoke a little bit about it, is how do you actually detect asteroids, right? How can one detect it? Now, asteroids can be relatively easily detected basically because of their shift. So supposing if you were to look at a patch of sky, okay, and as you take repeated observations of that part of the sky, you will see that the stars continue being at their location, but you will see a certain object moving. Like I'll show you in a picture soon of how do you actually see this kind of a moving object, which is an asteroid. And that is the very basis which is used, the principle which is used looking for asteroids, right? So, first of all, we'll cover what is called the NEO-WISE project. So, NASA had a mission called the WISE mission, which is a small telescope which was sent out in space, which basically observed in infrared bands. Now, asteroids are going to be good detectors in infrared bands because they are cold objects. So, their typical wavelengths where you'll get more radiation would lie in the infrared, and therefore the WISE mission, the WISE data, was actually then used to actually give measurements of asteroids and comets, and that was called the NEO-WISE project, which was based on the data of the WISE data. And it basically WISE data is available, and it basically uses WISE data to look for solar system objects, which can be very well found using WISE data. There's another spectroscopic data, which is called the BITHINOS, which is the MIT Hawaii Near Earth Object Spectroscopic Survey, which is basically, it is used to looking for, again, by large groups from Hawaii, MIT, NAU. And they are basically doing spectroscopy of these objects. And it's publicly available data, which is available through their website on spectroscopy of these objects. Now, along with this, there are many more survey projects which actually look for asteroids. So, for example, and typically for this, you need wide field telescopes, right? You basically want to look for a large field of view. You do not want a small field of view. You look for large parts of the sky and look for objects which are moving against the background of stars, right? And you can have a look at planetary defense asteroid hunters. And then once you detect such an object, it has to be reported to the Minor Planet Center. So, for example, some of these surveys include, there's a Catalina Sky Survey, which is conducted by the University of Arizona, which actually surveys the sky repeatedly. Similarly, there's what is called the Pan-STARRS survey, which is the Panoramic Survey Telescope and Rapid Response Center. So what the PanStar does is it kind of looks for transients. So what you have is you keep looking at the sky, you see the same parts of the sky repeatedly, and you look for transients. You look for objects which are changing in their brightness or in their positions. Similarly, the University of Hawaii has a project which is called the ATLAS, which is the Asteroid Terrestrial Impact Last Alert System. And the MIT Lincoln's laboratory has a linear mission, which is Lincoln Near Earth Asteroid Research. There are a whole set of these survey projects looking for these objects. Now, these NEO follow-up and characterization, this thing, what actually does is, if a survey actually detects a near-Earth object, then what happens is there are additional telescopes which are meant to follow up those observations. So, and you actually have to report this to what is called the Minor Planet Center and the Center for Near-Earth Object Studies, which is called the CNEOs. Okay, and it actually, why is that done? That is done so that one can determine the precise orbit of that object. So you basically have to observe the object very precisely and determine its observation, right? So there are many NEO follow-up characterization projects. There's University of Arizona Space Watch. The Las Cumbres Observatory is made up of a set of robotic telescopes which can observe all over the Earth for these objects. New Mexico has the other observatory, Lowell Observatory. And there are also radar projects which will use radars to actually look for these objects. So once you report having observed these kind of objects using whatever survey data, then it goes up for follow-up, where then we try to precisely find the orbit and predict the motion of that asteroid, right? To basically see whether there is an incoming impact or something which is, to happen in the future. Canada actually also launched a satellite, which is called the NEOSat, which is the Near Earth Object Surveillance Satellite, in 2013. And this was actually launched by an Indian rocket. The PSLV launch vehicle actually launched this 9 years ago. And the basic purpose of this satellite is to find asteroids closer to the sun than the Earth. Obviously, basically, these are 18s. These are the kind of satellites which are closer. And the problem is that these are very difficult to detect. Why? Because by ground-based telescopes, because of the atmosphere and the sun. So these are a bit too close for us to see because of that. And what NEOSat actually does, is it tracks asteroids it discovers. It also, along with this, tracks space junk as well as unknown satellites. So it can track all kinds of objects which are around, in orbit, and actually look for them. But it cost about 25 million, and you have it's a small one. It's about the size of a suitcase. It's at a height of about 800 kilometers, right? That's the height of the orbit for NEOSat. And then in last year, in June 2021, NASA has approved a further telescope, which will go out to space, which is called the NEO Surveyor, which would be a kind of improved version of the Canadian one, where it is again meant to basically look for potentially hazardous asteroids and comets that come within 30 million miles of the Earth's orbit. And this mission has been actually approved. It is still in the process, so it will still take some time, obviously, for it to get launched. But we are obviously looking for such objects. And then there is something which a lot of the participants in today's thing, I'm sure, have looked upon. Can you look at these images? So there is a software called Astrometrica, and there are various citizen science projects in which non-astronomers, people who are not professional astronomers, can also help in actually looking for asteroids, because these are important objects, right, which are essential for us. So if you actually see in this left-hand screen, what I was explaining in the beginning, how do you identify an asteroid? Now, I think you all can see it. Look at this object, right? This object, it starts off here. You can see that the stars are stationary, right? The stars continue being at their basic position. But you can see that this object moves. Now, Astrometrica is the basis of a citizen science project, which is on asteroid hunting, looking for asteroids. And many of you can actually participate in this citizen science project. There are regular calls for people who would like to join into the project. And you can see that what is basically given to participants is, on a weekly basis, you are given images. You are given images to inspect, And obviously the number of images coming from, say, Catalina survey or Pan-STARRS survey is very, very large. So the number of astronomers who are on the job are obviously much lesser than the amount required to look for an asteroid. So what happens is there are teams made in this, and the teams are given, members in the teams are given sets of images to inspect every week. So for example, if you had an image like this and you used Astrometrica software to actually blink those images and look for moving objects, you can clearly see that this is a moving object. So this is an asteroid, right? So typically, if you identify such an object in the images, you say, oh, I identified a potential. I mean, this is a candidate asteroid. The next step is that you report this object, right? So if you actually see, so this is just this thing. I had also participated in some such citizen science project. So Soban Acharya is the person in India who actually handles a lot of these groups. And I joined one of his group called Arundhati. It was an all-female group. And we actually looked for asteroids in data, right? And Patrick Miller also spoke to you 2 days ago on the thing. And that's how you can do it, look for asteroids. And then once you look for it, you actually have to report it to the Minor Planets Center. Now, the Minor Planets Center basically has data on almost 1 million minor planets in the inner and the outer solar system. And what they do is, for the data which you provide with them, you provide them that, we have found so-and-so object. So Astrometrica will help you getting various information about that object, its exact location and its parameters, etc. And you report it to MPC, the Minor Planet Center. And then if the reported object, if they're correct, then you actually get a catalog number. And whoever was the observer of the first apparition with the calculated orbit, he or she is declared the discoverer and actually granted the honor of naming the object. Okay. Now, how are these objects named? These objects are named with approval from the International Astronomical Union. So they have a certain way in which you actually name the object. But obviously, whoever is the discoverer that has some role to play in that, right? So this is a very interesting kind of a thing in which citizen science can also contribute. And there are various other citizen science projects which we don't have time to talk about today. But there are very many projects in which non-astronomers can also participate in important astronomical discoveries which are taking place. For the simple reason is that the astronomical data available is very, very large. It is obviously not enough to be handled by all the working astronomers. And therefore, it's very good if citizens also contribute into that in this process. So this is one example of asteroid hunting using Astrometrica, which is there. And then, for example, or in some cases, you can also, if you have a small telescope, right? If you're not even part of citizen science projects, if you have a small telescope, for example, there's an example of amateur astronomers which literally with a 3-inch telescope, they actually found the main belt asteroid, Amalthea. This is a known asteroid, but they found out that this asteroid probably has a moon. So they even identified the moon using their not very big telescope. And therefore, depending on the kind of skies you have in wherever you are located, one can also use a reasonably big telescope or a small telescope to actually look for asteroids yourself. But, there's obviously a large luck factor in actually finding these objects. And therefore, I'd like to conclude with this, that we have a lot of exciting times ahead. Like I mentioned to you, we have these various NASA projects where we are actually encountering asteroids. We are actually landing on them. We are crashing them. We are digging in them, getting material from them, which is being sent back to Earth for us to further study. There are many ways and many projects, many surveys in which we are actually trying to monitor these asteroids to actually keep track of where are they moving, what are their orbits, where are they headed, right? And so I would say that we have a lot of exciting times ahead with a lot of work happening on asteroids, playing a very important role in present day work in astronomy. And like I said, that this is specifically work in which not only professional astronomers, but even amateur astronomers can play a very important role. So I'll stop with this. And I'll be happy to take questions.
Yeah. So Thank you very much, madam. It was really wonderful talk, I guess. So the floor is open for questions. Participants, you can post your questions here. If anyone want to type in the chat box, you can use the chat box also.
I have a question, ma'am.
Yeah.
How to make a career? How to make a career in the field of astronomy, ma'am?
Yeah. Okay. So basically, for astronomy, you'll need to do physics, maths, and computers, right? So there are very many ways in which you can get into it. For example, the standard way is you'll have to do obviously physics and maths. Those are the most important subjects which you should do in your 11th and 12th standard. Your graduation also should have physics and maths. And then when you do a master's, you should have physics with it to do astrophysics. But on the other hand, if you would like, if you're more comfortable or happier with mathematics, you can also do astronomy from the mathematical point of view, which is, but that would be more of what is called celestial mechanics, where you are studying, for example, satellite launching, or it would be more into space research, and how exactly are satellites launched and things like that. But if you go from the physics point of view, then you could be doing then you will have to do your masters in physics. There are various universities and places in the country where you can actually do masters in physics as well as have a paper or two in astronomy. Where are you from, Sharon?
Ma'am, I'm from Tamil Nadu, ma'am.
Okay. So actually, I mean, even ISRO has its center in Trivandrum, which is called the IIST, which in which you can do an integrated PhD, which means a master's in astro with a PhD in that. Like I said, a lot of universities, for example, in Hyderabad itself, Osmania University is the only university which has an astronomy department, and many more universities, Delhi University, Pune University, Raipur, many universities do have it. A lot of IITs also have faculty who are from astronomy. So even IIT Bombay, IIT Indore, IIT Mandi, IIT, there are a whole set, even IIT Hyderabad also has some faculty in astronomy. So you can join there for a master's with engineering physics and then go in for a PhD. There are a lot of institutes in the country, which some of them which offer integrated PhD programs, but that would be an MSc PhD combined or a direct PhD. And for some of them, you can join in even if you have a BTech. So even with a BTech, you can apply for the integrated PhD program, right? So there are many ways in which you can actually this thing. You can actually check up websites of many of these institutes, and probably that will give you a good idea. I can see there are lots of questions on chat. So, Shritan, what happens when an asteroid enters the sun? Oh, that's the end of the asteroid because the asteroid is not going to survive on the sun. So actually, there's nothing. It would just be the end of the asteroid. Nothing much for the sun. It won't make a very big difference, but it will just get into this. Um, Bala Kaushik asked me, does asteroids radiate its surface material like dust, etc., while orbiting? So, like I said earlier, an asteroid is not a radiating, it's not a star. It's basically going to reflect. So, there is something called the albedo, which is, for example, the moon has a certain albedo, which is the amount of light it will reflect, right? So, depending upon the material the asteroid is made up of, how well it reflects, it may reflect the light which falls on it, depending on the dust, what is the composition of that material, it will actually radiate, right? So, but essentially, this is reflected light. So it's not going to be very bright. It would only be there when there's a specific alignment of the asteroid towards the Earth. And that's why, like I mentioned, most of the asteroids go undetected because if we want to detect them, they obviously have to be in a specific configuration so that light falls on them, gets reflected, and we see it, right? Otherwise, we won't be able to detect that asteroid. Amarpal Singh, thanks. Tushar, ma'am.
Good evening, ma'am.
Yeah.
May I ask one question, please?
I can see
Hello.
Tushar says, how can
Uh,
dropout school students do a career in astronomy? Tushar. So you'd have to continue studying. If you want to do astronomy, you have to continue studying. So you'll have to rejoin school and continue studying. complete your school, and then go in for a bachelor's and a master's and a PhD. So it means astronomy means obviously many years of study you'll have to get in this thing. Shritan is again asking me asteroid radiation. You don't have radiation from the asteroid, like I told you. It will only reflect light, and it will reflect light depending on its albedo, what its reflecting properties, right? Depending on that, it will reflect. Mohan says, I want to be a researcher in the field of astronomy. What should I do? You're in 8th standard, so you focus on physics and maths, study your physics and maths well, and continue with physics and maths as your subjects for graduation as well as post-graduation. Same for Mohan Kumar, focus on physics and maths and this thing. So there, Bala Kaushik, some books for astronomy and astrophysics. So there is a book called The Physical Universe, right, which is by Frank Shu, which is a very good book on basic astronomy. And I think that would be a very good book to start with. For people who are interested in more popular science types, a very good book would be Cosmos by Carl Sagan, right? And so Meenakshi Goel, what is the eligibility criteria to become a part of Women in Astronomy Working Group? So actually the Women in Astronomy Working Group, of which I'm the co-chair, it is of the International Astronomical Union. So the first thing is you need to be, all that you need to be is you need to be a member of the International Astronomical Union. And if you are a member of the International Astronomical Union, you are most welcome to join the working group. And to join the working group, you do not have to be a woman. So even men can join the Women in Astronomy Working Group. It's open to all genders. But you need to be a member of the International Astronomical Union. Right. Keshav says, how can I study astronomy after 10th? Yeah. So Keshav, you'll have to do maths and physics for your inter 11th standard and 12th standard. And then in graduation also, you'll have to continue with maths and physics, right? To a member of the Astronomical Union, so you'll actually, every year there is a call for membership. So the call for membership this year is already over, but every year you have a repeated call for membership of the International Astronomical Union. And then when the meeting is held at the International Astronomical Union every 3 years, they confirm membership of the people who have applied. So you'll have to, you can go through the website. I can show you the IAU website. So this is the, I'll just share the IAU website, and 1 minute. International Astronomical Union, IAU, yeah. So here is the website of the International Astronomical Union, and you can go through it and actually see when and how can you apply, right? Bala Kaushik asks, can you please elaborate about the thing, how researcher could think to discover something? It depends on what you want to discover, right? Like I told you, if you want to look for asteroids and you're a non-astronomer, then something like the Citizen Science Project on asteroid hunting is a good project to join. And with that, you can actually look for asteroids. So the whole thing is about what do you want to discover, because you need to study or familiarize yourself with that branch of astronomy well, so that you can work on it. So Astronomical Union, no, it is free. For IAU membership is free. The payment is actually paid by the country. So India actually pays for its IAU membership, and the members are then taken in by a selection committee. So a selection committee decides who are members, and they get taken in. That is for free. The country, India itself, pays for its membership in the IAU. And individual members like you and me, we do not have to pay for our membership. That comes free. Okay.
Good evening, ma'am.
Yeah.
Ma'am, my name is Chandana, ma'am. I'm from Tamil Nadu, Alchemy Public School, and I'm doing my 8th standard, ma'am.
Okay.
So this session was wonderful, ma'am, and this is my first session. So it was so nice. I loved it. My doubt is, what if any two asteroids got collided, ma'am?
So actually they do. Thank you. Thanks for your question. So actually asteroids do collide with one another. And instead that is the process due to which they've become so small, right? Because they are in this region between Mars and Jupiter where they were moving around and a planet did not form, and because you had all these small pebbles going around, they actually constantly do collide with one another. So collisions between them is very common, but obviously it depends on the composition of the asteroid. Some asteroids are made up of pure metal. So just think of it, you have two iron balls which hit each other and nothing much will happen, right? Because iron is solid. But some of them, for example, they're made up of carbon. Carbon could be softer, right? And if it is softer, they may break into smaller pieces. If they are, made up of much stronger material, they won't break. So it all depends upon what is the composition of those asteroids. Remember, I showed you different kinds of asteroids. Some are made up of carbon, some of them are made of silica, while some of them are made of metal. So depending upon what the particular asteroids are made of, that will define what will happen in case they collide, right? Yeah.
Okay, ma'am. Thank you, ma'am. Spending time with you was my pleasure, ma'am. Pleasure
Thank you.
time, ma'am.
Thanks a lot. Thanks a lot. Thank you so much. So Shehzadi Begum is asking me, um, uh, when are there certified courses? So there are lots of certified courses available on the net. You may be aware of what is Udemy, or there is what is called Coursera, right? I'm writing it down over here. There is Coursera, there's Udemy, there are MIT courses, there are many more online MOOCs or courses which are available on the internet. And depending on your level, right, whether you're in school or you're in college or you're in university, depending upon your level, you will actually have to look for the required courses. But there's lots of material available on the net. So if you actually search, you would be able to quite easily find courses. There are many courses available, so you will actually find a lot of them. Tushar is asking about when registration happened for members of Astronomical Union. I think that happened sometime in January. So generally it happens about 6 months before the General Assembly of the International Astronomical Union. So the General Assembly of the International Astronomical Union meets very regularly. So if you can actually see this over here, they actually meet very regularly. And before the meeting, they actually have a call, right? So it happens often enough. Okay. For school students. So for school students, I'm not too sure of a course, but there are lots of websites which I can actually look for astronomy courses for. So yeah, so for example, this one has a course I'm sharing with you, which is called, let me share my screen. I'll share my screen. I'll share a window and I'll show you this. I hope you can see this thing over here. So for example, this is Udemy, which has a backyard astronomy course on stargazing, right? And you can actually have a look at this course. For example, there are many more courses getting started with astronomy for beginners. Some of them are paid courses, some of them are free courses. You can see this is spherical astronomy course, tour of the solar system, and various courses like this. You can actually find it. These ones are paid ones, but I'm sure there are a whole lot of astronomy courses which are even free courses which you can find. So you can actually see there's this futurelearn.com, which also has short online courses. And in this, I hope there is something on astronomy. I don't see it over here, but you could probably find some online courses. So I think you just have to search for it a little bit, and I'm sure you'll be able to find some. Okay. So Amarpal Singh wants to know about the vaporization of small solar system bodies like asteroids. So what basically happens is that these small bodies, they enter into the Earth's atmosphere. Many of you all would know about the Challenger disaster, right? Challenger was a space mission which was, when it entered into the Earth's atmosphere, that's when, because of friction, right, there was a problem with the insulation system on that, and therefore what happened is that thing just got fired and it got finished, right? So typically what happens is, if you have these small solar system orbits which enter the Earth's atmosphere, there's a very large amount of friction, and because of friction, that material, the meteor, actually gets it becomes molten, it burns, and it actually burns off in space. And that is what is called a meteor, or that's what we call a shooting star, right, which we can see. You can see a light up in the sky which kind of goes off, right? And that is what is called a shooting star. But some of them, if they are more massive, they don't get totally vaporized, and then they fall on the Earth, and that is what is called a meteorite. But otherwise, the bulk of them get vaporized out in space, in the atmosphere only, because of friction, and that's when they burn off, right? So Mohan Kumar, you have a question. We know that asteroids are between Saturn and Jupiter. Then what is the need to search asteroids? Okay, so Mohan Kumar, I said the asteroids, the bulk of them are between Mars and Jupiter, not Saturn and Jupiter, but Mars and Jupiter. The reason we need to search for asteroids is because some of them, the solar system has many massive planets, right? And therefore, some of them, instead of being in that orbit between Mars and Jupiter, they can get into the Earth's orbit. They come closer to the Earth and they can actually fall onto the Earth, right? Some of the asteroids. And these are the ones which are obviously important and interesting for us, because we would like to know if there is an imminent impact which is expected because of an asteroid getting into our atmosphere, right? And therefore, we need to search for asteroids, because we are basically looking for what are called potentially hazardous asteroids. Like I told you in the very beginning, we are celebrating Asteroid Day, or June 30th, specifically because that marks the anniversary of the Tunguska event. The Tunguska event is when an actual meteorite fell on to the Earth, right, which created a lot of damage. And that's why we are concerned about any possible such thing which can happen, which will damage the Earth, right? And that is why we would like to monitor asteroids to check whether is there something which we need to be careful of. And that is why I explained to you, for example, that DART mission, where the attempt is basically to check and see that can we in some way avoid this thing from actually coming onto the Earth, right? So Neela Sikaran as well as Shritan are asking, what would happen if comet hit the Earth? So a comet or an asteroid, something like that, if it were to hit the Earth, obviously it would mark a lot of devastation onto the Earth. And like I told you, there would be what is called a nuclear winter. So it could impact the Earth, throw out a lot of dust, right? And the dust will form a blanket around the Earth, which will stop solar radiation from coming onto the Earth. And therefore, what will happen is the plants will not be able to do their photosynthesis and produce their material. So animals which depend on plants will not survive. And also the animals which depend on those animals which depend on plants will also not survive. So that could lead to a mass extinction. So, but how prepared are we for it? We are not very prepared for it. We are trying to prepare ourselves, like what I told you with the DART mission, where they're trying to see whether we can deflect an asteroid. There are various ideas which people have of how can we actually avoid an asteroid impact through a missile or through a deflection of some kind. Or there are various, strategies which people describe. Some of them seem possible, but the bulk of them are not very, they don't seem very possible. So as of now, we do not know very well how to actually protect ourselves, but we obviously need to work towards it and actually look for a method in which we can, actually protect the Earth from such an event, because such an event could be very devastating. It could be this thing, like the one described in the movie. Yeah. Shankar, please answer my question. I'll just look for your question. What is in Saturn's rings? So Saturn's rings are also such small objects, which there could be two things. Either it was a planet which was going around Saturn. The problem is it's close to Saturn, and Saturn is very massive. So it's possible that it was a planet which either could never form because of, because Saturn was so massive, in its proximity, you could not form such a large planet. Or it could have been a planet which formed but then got broken up, maybe because of collisions or some other thing which happened, which actually broke it. So Saturn's rings are either a planet which formed and broke, or a planet which never formed because it could never, because of Saturn's gravitational force. This thing, right?
Okay. I
I
think there are lots of questions.
yeah, there are many more.
Yes, madam. So really, it was a wonderful question answer session as well. After your talk.
Just a minute. You all can continue putting your questions on YouTube, and I'll answer it over there, right? So that's for the others who still have questions. Please add them on the YouTube thing, and I'll answer it. I promise.
Yeah, sure.
Yeah. Okay.
I may share the YouTube link later. Just completing the vote of thanks, I guess.
Yeah.
So really, thank you very much for your wonderful time, madam. We really enjoyed. Participants, I think, really enjoyed, and they have lots of doubts and questions. So once again, thank you very much for your wonderful time and in the evening. So this is our 4th Asteroid Day talk. We have upcoming sessions in our list. So do join us. Tomorrow we have a wonderful talk from Dr. Sailaja, who is a visiting scientist at Jawaharlal Nehru Planetarium, Bangalore. We welcome you all for that talk also. So now it's time for thank you once again. Thank you very much, Dr. Priya Hasan, and thank you very much for all the participants for your wonderful. Yeah, thank you very much. I will share the YouTube link in the chat box.